Hello everyone and welcome to another video. In this video, we will be covering some basic differentiation rules. So unlike the previous one, we won't be using the limit definition anymore. We won't be differentiating from first principles. We will just be using rules that have already been established through first principles and applying them to different functions. And by doing this, we'll be saving a lot of time. And these techniques are accepted on exams. You don't have to use first principles to differentiate everything. So the first rule that we'll be looking at is called the constant rule. And it says that if f of x is equal to just a constant, then its derivative, f dashed of x, is always going to be equal to 0. And it doesn't matter what that constant is. So this constant can be 5 or a million or pi, whatever. It doesn't matter what it is, the derivative f dashed of x is always going to be 0. At every single point, the gradient will be 0. And the reason for that is because this is a way that a constant function looks. Okay, it's just a straight line. If you have f of x on the y-axis and x on the, x-axis, then since the function is just a constant, it's going to be the same value for every x. And there's no change in y, so the derivative is going to be 0, because remember, f dashed of x is the change in y divided by the change in x, where d stands for difference. So if the difference in y is 0, then the derivative will also be 0. And what a constant means, essentially, is that it's independent of x, the variable, so it's just a number. Now, the next rule is the constant coefficient, and it says that if f of x is a constant times another function g of x, okay, then the derivative of f, so f dashed of x, would be equal to that constant times the derivative of g, so g dashed of x. So you can kind of pull the constant out, okay? The constant stays and you're just multiplying by the derivative of g to obtain f dashed of x. Now for the sum of functions, where we'd have f of x equals u of x plus v of x, and now u of x and v of x can be any functions really, they can be a power or a division, whatever, then f dashed of x equals u dashed of x plus v dashed of x. So you can kind of distribute the derivative to both functions. It doesn't matter that we're adding them. Now, for the power rule, it states that if f of x equals x to the power of n, then f dashed of x equals n times x to the power of n minus 1. So what's important to remember for this one is that n has to be a constant. It must be independent of x, okay? So if you have something like f of x equals to x to the x, okay, you can't just use the power rule, because that would tell you that f dashed of x equals to x times x to the power of x minus 1, okay, if we were to just apply this rule. But this is false, okay, because the power is dependent of x. The power is x, so it's also dependent. And if you have x in the exponent, you can't use the power rule. The power rule is only valid if this exponent n is a constant, meaning just a number that's independent of x. So the way to remember this rule is just that in the derivative, this power n comes down as the coefficient, as you can see here. And then x, we still have x, but its power is 1 less. So instead of n, it's going to go down to n minus 1. So if we start with x squared and we differentiate it, then this power, n, is going to come down as the coefficient of x, and then x will be raised to the power of 2 minus 1, which is just 1, and x to the power of 1 is just x. So the derivative of x squared is 2x, okay? And we showed that in the very first video, I think. So yeah, these rules with the constant coefficient and the sum of functions, we did prove them with the limit definition in the first video, so if you're interested in the proof, you could take a look at that. But we're not going to actually prove any of the other rules using the limit definition. We're just going to apply them. And finally, there's one more rule that we should cover before moving on to exercises, and that's the chain rule. It's a bit more complicated, but it deals with composite functions. So if you haven't encountered composite functions, you should probably watch a video on that first. We will probably make one in the future. But for those who do know what composite functions are, if you have f of x being a composite function of u and v, so f of x equals u of v of x, okay? How would you find the derivative of that? Well, f dashed of x equals to the derivative of u with respect to v times the derivative of v with respect to x. And this thing here that we're multiplying by, we call that the internal derivative because it's the derivative of this internal function v, where u is our main function. So just to quickly do an example, imagine we had 2x plus 1 and all that to the power of 4. Okay, we could say that u equals to v to the power of 4, and v is a function of x, which is equal to 2x plus 1. Okay, so if we were to plug in this v into this v over here, we would indeed get our main function. Okay, so now if we were to just apply the chain rule, we would get, so we have u dashed of v, so we have to look at this over here, and we can just apply the power rule. U dashed of v is going to be 4 times v to the power of 3, because 4 minus 1 is 3. But then we have to multiply by this internal derivative, v dashed of x. And v as a function of x is 2x plus 1, so we must find the derivative of 2x plus 1. And the derivative of that is 2, using the constant coefficient rule. Okay? And now we can evaluate 4 times 2, that's 8, and we're multiplying by v cubed. And we can rewrite this as 8 times 2x plus 1 cubed, because v is just 2x plus 1. So that's how you apply the chain rule, but we'll do more examples in a bit concerning the chain rule. Okay, so the first example is f of x equals 5. Now 5 is just a constant, it's independent of x. So using the constant rule, we know that the derivative is just 0. The next function is f of x equals e to the power of pi. And I don't use the power rule just because you see a power. That's only for when you have x in the base. Here e is just a constant, and so is pi. So e to the power of pi will also just be a constant, making the derivative 0. Now the next function is f of x equals to x. And this one you should remember its derivative by heart. But to do it properly, you would use a power rule. You can write f of x equals to x as just x to the power of 1, okay? And then you'd bring the power, making it the coefficient, so that would be f dashed of x equals to 1 times x to the power of 1 minus 1, which is 0. And x to the power of 0 is just 1, and 1 times 1 is 1. So the derivative is equal to 1. Okay, we have f of x equals 7x. Now we can use the coefficient of a function rule that says the derivative of this whole thing is the coefficient 7 times the derivative of this thing, which we established is just 1. So that's 7 times 1, which is 7. Okay? So whenever you have f of x equals to some constant times x, then the derivative is just k, the constant. Okay. F of x equals to 2x plus 3. So we have a sum. Okay, we have a sum. So the derivative of the whole thing is going to be the derivative of this plus the derivative of this. The derivative of 3 is just 0 because 3 is a constant. So we can ignore this part and just write down the derivative of 2x, and that'll be our final answer. The derivative of 2x is 2. Next we have f of x equals x to the power of 5. This is just a simple application of the power rule. So the exponent comes down as the coefficient, and then we still have the x, and the power will be 5 minus 1, which is 4. So 5x to the power of 4. Next we have f of x equals to 2x plus 5 to the power of 60. Now if you were to expand this into a very big polynomial, that would take a very long amount of time. So why don't we use the chain rule, since we have a small function here, 2x plus 5, and then the other function would be raising that to the power of 60. So we can say that f of x equals to v of u of x, okay, and v equals to u to the power of 60, and u equals to 2x plus 5. Okay, so let's determine the derivatives. V dashed is 60u to the power of 59 using the power rule, and u dashed is just 2, because the derivative of a constant is 0 and the derivative of 2x is just 2. So I'm going to bring this down here. Now the chain rule states that the derivative of f, so f dashed of x, is going to be v dashed of u, which we established is 60 u to the power of 59, and I'll just write u as 2x plus 5 because that's what u is. So we have it to the power of 59. But then we still have to multiply by this internal derivative u dashed. And multiplying by 2 is going to turn this 60 into 120. Okay, so our final answer is going to be 120 times 2x plus 5 to the power of 59. And now I'm going to delete this. So the next one is pretty similar. We have e squared times x plus 1 to the power of 10. Okay, so e squared is just a constant coefficient of this main function over here. So we can just take the derivative of this main function here and then just multiply it by this constant e squared. So let's first take x plus 1 to the power of 10 and determine its derivative. Now this one is, again, pretty similar to the previous one. It's just a chain rule. So let's say this is our function g of x. We can't say this is f of x because we've already defined f of x to be that times e squared. So we'll say this is g of x, and we'll say that g of x is a composite function v of u of x, okay? So v equals u to the power of 10, and then u would have to be x plus 1. Okay, so taking the derivatives, we get v dashed equals 10u to the power of 9 using the power rule, and then u dashed is just 1 because, yeah, this constant, its derivative is 0, and the derivative of x is just 1, and when we add them up, we're just left with 1. So this internal derivative u dashed is equal to 1, and we're multiplying by it, so it's not going to have any effect. So the derivative of g is just going to be this 10u to the power of 9 via the chain rule, and we can write this as 10 times x plus 1 to the power of 9 because u is just x plus 1. And now remember, for our original function f of x, we're multiplying this whole thing by e squared. So the derivative will be 10e squared, okay, 10e squared times x plus 1 to the power of 9. Okay, next up, we have a function which is equal to x squared to the power of 3, all that to the power of 4. And we can use exponent laws to rewrite this as x to the power of 2 times 3 times 4, which is equal to x to the power of 24. And this is, again, just a simple application of the power rule. So we get that f dash of x, the derivative, will be equal to 24x to the power of 23. So the power becomes the coefficient, and then the new power is 1 less. Okay. The next function is 5 over x squared. We can rewrite this as 5 times x to the power of -2 using exponent laws. If you're not familiar with some of these exponent laws, we might make a review of exponent laws soon. So yeah, if that video is up by the time you're watching this, feel free to check it out. But yeah, this step is correct. 5 over x squared is equal to 5 times x to the power of -2. And here we see a constant times a function. So we can just say that the derivative f dashed of x is just equal to this constant 5 times the derivative of this thing. And it doesn't matter that we have a negative exponent, we can still do this. So the exponent becomes the coefficient of x. So we're going to multiply by -2 and then raise x to the power of 1 less than the exponent. We're subtracting 1. So it's going to be -3 here in the exponent. And you could rewrite this as -10 over x cubed. Again, using exponent laws and multiplying 5 by -2. Okay, next one. We have f of x equals to pi over x minus 1. And again, keep in mind that pi is just a constant. And we can rewrite this as pi times x minus 1 to the power of -1. Again, using a similar exponent law. So the constant, for the derivative, the constant will just be copied, the constant being pi. And then this -1 becomes the coefficient. So it's going to turn this into -pi times x minus 1 to the power of -2. Okay, because we're subtracting 1 from the exponent. Now, what we did here was a bit different because we just treated this as sort of as just x and then just wrote x minus 1. But if you were to use the chain rule, which you are supposed to do, you would get the same result. I just skipped the step. And you would have to multiply by the internal derivative of x minus 1, since that's your internal function. But in this case, the derivative of x minus 1 is just 1, and it doesn't make sense to multiply by 1. But you can show this multiplication by 1, just to be clear. And then you could also rewrite this as -pi over x minus 1 squared if you wanted to, but you don't have to. This form over here is simple enough already. And now just to show, if you wanted to use the chain rule to find the derivative of this, ignoring the pi multiplicator at the front, you would say that, well, let's say this function is then you'd say g of x equals to v of u of x, where v equals to u to the power of -1, and u equals to x minus 1, and then you'd find v dashed and u dashed, and you would just use the formula, and in the end you would get the same result over here. I just took a shortcut, and you should get used to these shortcuts as well, because in an exam you won't have time to show all the steps of a chain rule application. So you just have to always remember to multiply by this internal derivative, which in this case is 1, but won't always be 1. The next function is a ratio, and you might be tempted to just say that the derivative of f is just the derivative of the numerator divided by the derivative of the denominator, but that's actually not true. There is a quotient rule for divisions that we haven't seen yet. It'll probably be covered in the next video. But that rule doesn't say that you can just take this derivative and multiply it by the derivative of this. It won't be, that won't actually give the correct derivative function. But here we can actually find the derivative without applying any sort of quotient rule, because you see that you can factor out a 2 from the numerator, and that will give you a perfect difference of 2 squares. So if we factored out a 2, the numerator would be 2 times x squared minus 9, and then factorizing this would give 2 times x plus 3 times x minus 3, and then these brackets will cancel out with these. Okay, so in the end, our function is just equal to 2. Okay, so if our function is equal to 2, let me just rewrite this. Then that doesn't mean that the derivative will be equal to 2. Our function is equal to 2, which is a constant, so the derivative is equal to 0 by the constant rule. Okay, for the next one we have this long polynomial to differentiate, and differentiating polynomials is actually pretty easy, especially if they're in a form like this, because you just have a bunch of sums. So for the derivative, we can differentiate each term separately. So we can differentiate x to the power of 4, and then add the derivative of 2x to the power of 3, and then add the derivative of 3x squared, and so on. So differentiating x to the power of 4 will just give us 4x cubed by the power rule, and we'll be using the power rule for almost all of these terms. Then the derivative of x cubed is 3x squared, but we're multiplying by 2 by this constant. So in the end, it'll be 6x squared. And then the derivative of x squared is 2x, but we're also multiplying by 3, making the derivative of this term 6x. And then the derivative of 4x is just 4. And the derivative of the constant 5 is just 0, which doesn't have any effect, so I'm not going to write it. So that's our final derivative function. And finally, the last example is f of x equals to x minus n to the power of k plus 1 divided by x minus n to the power of k. So a few things to notice here. We first have to identify the independent variable, and that's x, because it's specified that the function is a function of x, not of n or k. And that tells us that n and k are both just different constants. Okay, so since we have the same base, we can apply exponent laws, and we can rewrite this as x minus n to the power of k plus 1 minus k. And the k's in the exponent cancel out, so that's just a power of 1. And a power of 1 doesn't have any effect, so this is just x minus n. And n is, remember, a constant. So the derivative, f dashed of x, will just be the derivative of this, again, since n is just a constant. And the derivative of x is just 1, so that's also the derivative of our entire function. And keep in mind there are some conditions on this function that I haven't specified, but for example the denominator can't be 0, and yeah, it can't be 0 to the power of 0 either. So yeah, there are some conditions to keep in mind that I haven't written down here, but they're implied. So thank you for watching this video, and in the next one we'll probably be covering some further differentiation rules like the product rule and the quotient rule, and then afterwards maybe we'll probably do some derivatives of exponentials, logarithms, trigonometric functions, and so on. So thanks for watching.